Today we learned that Young measures has nothing to do with youth or old age, rather they come from the name of mathematician Lawrence Young. Young measures are a way to make sense of convergence of sequences of functions when they do not really converge. And I will try to explain the main idea behind this. It's quite not that easy to develop an intuition for them, but at least the definition should get us started. We're not planning to do anything with Young measures, but well, everyone has been asking what are Young measures, where does the name come from? So here is the answer. So the motivation is from calculus of variation. Most problems you turn into minimization problems. For example, the problem of finding harmonic functions boils down to minimizing the Dirichlet energy. So you have a given omega, given boundary restrictions, and you want a function among all of them for which this becomes a minimum. So the infimum becomes a minimum. So if you want the one function that minimizes this, well, from definition of infimums, there exists some sequence of functions so that this energy for them converges to the infimum quantity as j goes to infinity. Now, the dream is that out of these sequences, probably after passing to a subsequence, you find, in some suitable sense, a limit function u. And you hope that this quantity, let's say this energy of u, is continuous or lower semi-continuous, so that you can deduce that this energy of u will be less than or equal to the limit of energy of these uj's, and because they converge to infimum, so this will be equal to the infimum. Therefore u will be your goal minimizing function. Unfortunately, there are interesting examples of energies which do not have all of the properties, and you can end up with minimizing sequences that do not converge in the usual sense. But still, you want to make some sense of the behavior of these functions to understand your minimization problem better. So those were the applications and examples were listed in that Wikipedia article. So calculus of variations, optimal control, PDEs are where this occurs quite often. So the fundamental theorem of Young measures is showing that in some sense, every bounded sequence of measurable functions has a limit. And this is very general, so this limit, unfortunately, will not be a function, but quotation mark, a measure. So the theorem reads as follows, and you will see that it has very weak assumptions, so it's quite impressive. So omega is a domain in Rn that is bounded and measurable. I said domain, but I don't think that's even necessary. We don't need open connected set or anything. Let uj from omega into Rm, m equal 1 is already interesting, but be measurable and bounded. So each one of these uj's is a bounded function. Because we're talking about measurable functions, we use the fancier L infinity notation. So this be bounded and also uniformly over all j. So this be not infinity. So you have a measurable bounded sequence of measurable functions on some domain. Then there exists some subsequence of the original sequence, and there exists some association of measures to every x in. There exists Vx, which are Vx is a probability measure. So it's a Rodin measure and the measure of all our m is equal to 1. So this is why it's called probability measure. It really doesn't have anything to do with probability. So it's a Rodin measure with mass equal to 1, which is just always doable after normalization. Okay, so to every x you associate a measure. So these measures are measures on Rm, this target of your functions, such that. So remember, the idea is to compensate or find an alternative for convergence when there is no convergence. So if you, so we will write a condition and we will require that for all suitable test functions from a big class of functions, for example, it must include compactly supported continuous functions for all functions phi. So these phis are two variable functions, so phi of x and a second variable. So here we put, so let me see if I'm consistent with my notation. Great. So u j k of x. Okay, we want this limit as k goes to infinity. So suppose you are you're talking about a continuous in both variable function phi. So if ujk converge to some value, say ux, then this limit would obviously be just equal to this, right? So if ujk do not really converge and they oscillate, the way for them to not converge because they are bounded is to oscillate. So then they visit many different values. So they visit many different lambdas for Rm. So these are mapping into Rm. So x is fixed, but as k changes, these functions visit many different lambdas. If they all visited one lambda, of course, the limit of ujk would be lambda. So now that they keep jumping around here and there, we average them. And the averaging is against this measure. So remember, x is fixed at this moment. We're looking at k. So we have this probability measure on Rm, and then we integrate against it this quantity. So, for example, if these ujk's never visit neighborhoods of lambda equal 3, this measure would be a measure that is 0 around lambda equal 3. So that's how you should think about it. And then we said averaging, so integrate. So first, average these phi x lambda quantities when lambda runs over all of our m. This captures all values that ujk's meet. But the requirement for these Vx to be the Young measures, so these will be called the Young measures associated to this ujk, is even weaker. We don't want this to really happen for every x. Again, we want this, which is already in an average sense, to be true only on average. So we integrate these quantities now, which depend on x, on just the Lebesgue measure integral. Okay, and comma. So then the claim, this is a claim, this is a theorem, that if you just have only bounded sequence of measurable functions, you can go to a subsequence so that then you can associate to every x quantity, or we can say for almost every x. There are delicate issues there. Okay, let's focus on the main idea. So there are these probability measures, one measure per each point in lambda, in omega, sorry, so that this limit equality claim holds. So then we say that this Vx are the Young measures associated to this subsequence. Of course, you may have a different subsequence and then end up with a different Young measure. So it's not unique for the uj, but it's unique, of course, for ujk. I had been trying to understand Young measures for some time without much success, but I found these notes finally from Marcus Webb and Philip Rindler. These are 19-page notes, very carefully and beautifully written. The reason I'm saying they are carefully written is, for example, this they have made precise this idea that this association of measures, well, this is for every x, we associate an element from the set of all probability measures on our M. So suppose this is all probability measures on our M, and this association is just a function. So they have made precise this notion that this V is itself measurable. Of course, for this, we need a lot of background. But this is just to give you an idea of how nicely these notes are written. And one difficulty about Young measures, I mean, it's not difficult, right? This is very nice, clean. If you've dealt with measures, this isn't really that hard. However, the difficulty is trying to interpret and make sense of it. So we keep trying to say, what are these doing? Are they averaging the UJK values? Are they looking for how often UJK hits lambda? So we can always philosophize, and to some degree something is true and to some other degree false. So these are not really mathematical statements. They are not true false values associated to them. So you can try to build intuition. Depending on context, people have tried different things. They have given purely probabilistic interpretation. There is another interpretation which goes back to Young himself, where if you have a function, then it has a graph, and then you have the measure, which is restriction to the graph, and then these UJKs, these measures converge to something. So there are many different interpretations, but of course no one is always capturing all behavior. So ultimately, it's just measure theory. But initially I explained that if these UJKs really converge to some one unique value, for example, if UJKs are just constant, they are all the same function, then obviously your formula that you want to have hold this thing would work if you replaced all this inside with just, if you replaced all of that with simply phi of x and that limit ux, say. So in this case, we see that if you take Vx to be the delta drag at ux, then this integral will end up with that one. because this will be non-zero precisely only when lambda is equal to phi of x. So when you replace lambda with u of x, you will hit the measure equal 1, and you won't care about any other lambdas. So you see again that if you really truly have convergent subsequence, then these Young measures do exist, being the delta Dirac function. More generally, much more is true, and this theorem again from that reference from Webb, that if you have a sequence of functions that converge in measure, which is even weaker than pointwise convergence or uniform convergence, if and only if the Young measure associated to them is the delta Dirac function. So of course these Young measures is not one measure, it's per every x, so this x appears here. So this is an indication that it really generalizes the usual convergence, but then there are many examples where we have convergences that are not obvious, or we cannot interpret in the classical sense. Let me go back to Wikipedia and give you an example. One example is that, so you have sequence of sine nx. In the PDF reference I mentioned, this is done for all dimensions and not just sine function, any function. You fix one function ux, and then you create u of jx to be your uj sequence, and there they compute the Young measure associated to them. But anyway, so the Young measure for every x will be given by this formula. So the Young measure of, to tell you what a measure is, it's enough to say what is measure of a set. So if you have a Borel set, say E, the Young measure Vx of that set will be equal to integrating this weight in the -1 to +1. And notice it's restricted to -1 to +1 because none of these sequence elements ever go above or below -1 and 1. The fact that this weight is the biggest near the +1 and -1 is quite interesting. So as I said, it's really difficult to philosophize or build an intuition for this. Does it really say that this sine nx visits +1 and -1 more often? I have no idea, because this sine x and x visits all values, but how often or how likely it is to visit each one, again, I'm not sure if this is telling that or something else. But anyway, that is the story of Young measures. And but of course, the other interpretation is that people watching this are often young mathematicians. Whatever reasons you have for following this channel, thanks a lot, and see you in the future video.